Hello, my name is Gerardo Gutierrez. I'm from Evolution Engineering, Design and Energy Systems, and I will present my research on site selection and performance analysis of photovoltaic plants in the coast of Ecuador. First, as an introduction, we'll talk about that the electricity in Ecuador has a high renewable share but has a low diversification. There is a high dependence on hydropower that has led to energy crises in the past. The government is aware of the problem and is promoting new sources of renewable energies. Thanks to the geographic location of the country, it is a good candidate for solar power. The average radiation is of 4.5 kilowatt hour per square meter per day, and the country has a constant of 12 hours of sunlight throughout the year. The objectives of the research were to propose photovoltaic power plants in the coastal provinces of Esmeraldas and Manabí, to determine the best locations with the use of geographical information systems and multi-criteria decision-making algorithms, and to simulate different systems with the available technology in the country. The Ecuadorian energy mix, it's composed by 60% of hydropower, 37% of non-renewable thermal energy, 1.9% of biomass or biogas, 0.3% of solar photovoltaics, and 0.2% of wind power. There were droughts in 1993, 1995, and 2009 that caused huge blackouts and had an impact on the economy. The government has set preferential rates for alternative renewable sources for plants up to 15 megawatts, with two main objectives. One is to promote the non-conventional renewable energies, and the second to promote the development of local technologies. Currently, there are two Ecuadorian module companies. One is called IAPE Renewable, which is Ecuadorian but manufactures its modules in China. And the second one is Eco Energy, that makes amorphous silicon modules in Quevedo. Ecuador is located at the equator in the northwest part of South America. The Esmeraldas and Manabí provinces are located at the northwest coast of the country. They have a combined area of 34,400 square kilometers. They have a constant temperature throughout the year between 20 and 32 degrees Celsius with a tropical climate. And the reason to choose these two provinces is because on April 2016 they were hit by a 7.8 in the Richter scale earthquake that caused the destruction of the entire towns in both provinces. The government has put lots of efforts in the reconstruction of the site, and the construction of power plants could be among these plans. The demography of the provinces are as following. They have a combined of 1.8 million people. They have a high access to the grid, between 87% in Esmeraldas and 90% in Manabí. They have an energy demand of 1,600 gigawatt hours per year, but have a really low renewable share. In Esmeraldas, everything is produced by non-renewable energy, and in Manabí, they have a small photovoltaic plant that produces 0.75% of their energy demands. Also, these two provinces have the highest energy losses in the countries, between 23 and 24%. For the site selection, two techniques were used. The first one is geographical information systems, which are a set of tools to handle, display, process, and analyze large amounts of geographical, spatial, and attribute data, and multi-criteria decision making that is used to solve problems involving multiple variables that are not correlated directly to each other but have an influence on the final outcome. The considered variables were the following. For solar, the radiation and temperatures of the sites; economical, the proximity to roads, the grid access, and the closeness to consumption areas; for geographical, the use of land and slopes; and the restrictions that were set were lakes and rivers, national parks and protected areas, and cities. Each of these variables were assigned a weight, and each of the categories were also assigned a weight. The results were the following. Two sites in Manabí were proposed, Jaramillo and Vuelta Larga, and another one in Esmeraldas called Camarones. Now, talking about cell performance in tropical conditions. First of all, I would like to introduce the Stabler-Wronski effect, also known as the light-induced degradation. Amorphous silicon reduces their efficiency when they are exposed to light. There's a rapid reduction at first, but they tend to stabilize over time. And the manufacturers tend to rate the modules with the stabilization value rather than the initial power. So in the first year, the output is always higher than expected. As it is well known, for crystalline silicon, the high temperature reduces the open circuit voltage as the thermally excited electrons begin to dominate the electrical properties of the semiconductor, reducing its efficiency. But on the other hand, high temperatures on amorphous silicon recover partially the light-induced degradation. There's an increase in the carrier lifetime and the spectral band gap, and a decrease in the band gap, making it more efficient at higher temperatures. For the simulation, 5 models were chosen: the amorphous silicon produced in Ecuador, the monocrystalline silicon produced in China by an Ecuadorian company, one monocrystalline panel produced in China, a polycrystalline panel made by the same company in China. These 4 modules are found in the Ecuadorian market, and that's the reason they were chosen. And another one that's produced in Germany and cannot be found currently in Ecuador, but it is simulated to see the effect of the technology of amorphous silicon with hydrogen tandem cells. So the average performance ratio of these modules are the following. The lowest one is the polycrystalline silicon with around below 79% of the performance ratio, then followed by the amorphous silicon, then the Chinese monocrystalline, followed by the Ecuadorian monocrystalline, and the highest performance ratio was achieved with the German module. For the final yield, similar results are found that range between 59 gigawatt hours up to 66 gigawatt hours per year. For discussion and conclusions, there's a great potential at this site with a PR in the range of 0.79 and 0.87%. Up to 60 gigawatt hours per year could be produced. The impact is of building the farms are bigger in these provinces, considering the high losses of the energy mix and the social issues brought by the earthquake. And the plants could produce 4.4% of the energy in Esmeraldas and 3.25% in Manabí, with losses being reduced up to 7%. Also, local amorphous silicon performance is comparable to monocrystalline technology. The limitations that were not studied are the economics that will play an important role in sizing the technology selection and the feasibility of the build of these plants, and also the temperature weight on the multi-criteria decision techniques. The temperature was considered negative, but for amorphous silicon would be positive, so new sites could be considered. And that would be it. I thank you very much for this. If you have any questions, please send them to my email. And here are the references used for this presentation. Thank you very much.